too many of us now are having to spend too much time, especially in this country, in telling politicians that what we do cannot be predictable in terms of producing commercial benefit or health benefit. I must say that everything we showed is a perfect example. If you go back 40 years and ask the people, or 50 or 60 or 70 years, and ask, for example, Heisenberg, whether he thought the things he was going to do were going to produce benefits for humanity, like you showed. I need a copy of your talk to give to our Minister of Science. Quite frankly, he will continually tell us, if you can't tell me why you're doing this work, which of course Heisenberg couldn't, apart from it was rather important to physicists, he ought to learn this sort of stuff.
But you see, the great mysterious in magnetic resonance tomography is not that the scanner works. The great mysterious is that the politician gave the money to develop this scanner.
But thank you, it was very interesting. Anyway, what I want to do is, if I may bring you down to earth a bit, I'm an experimentalist, but as you've heard, because it's been throughout the media, we have in the last month, my colleagues have, actually had a lot of news pouring out into the media concerning essentially what I consider to be a piece of the most fundamental level of progress in our way of thinking about the world in terms of fields. And as an experimentalist, it got me thinking over the last 2 or 3 years, while my colleagues were building an experiment and I was doing a different experiment, in terms of what we're actually really doing and how important it is beyond just the normal mantra that's put out by labs and so on. So I really ended up suddenly being asked by Peter, would you like to speak? What do you want to give as a title? Fields in Action came to mind with a question mark. From the inside looking out, because as an experimentalist, I begin to see exactly what, in my working lifetime, which is coming to its end, in the sense of I'm not as young as I used to be, what in fact has changed in terms of a fundamental way that we look at the world of physics, the way we understand the universe and the things going on around us. And in preparing this talk, one naturally comes up against words that pop up when one looks for quotes and so on and so forth, and these two popped up, which of course come in completely different contexts. What I want to talk about first is seeing the action. Now in that sense, I want to start just by running through what we talk about as particle physicists. What are the terms in which we work, the degrees of freedom, if you like, of the laws of physics as we see them now. And without question, we work with the concept of fields, which implies we accept the idea of action at a distance, and that still means instantaneous action at a distance between two spatially separated points at the same moment in time. There is correlated action. Local gauge invariance is a feature of the mathematics, as I'll come back to every now and again, that drives the principles of the way we write down the laws of physics. Quantization, of course, is there. Flavor is essentially that which labels objects, quanta, in the field theories that we work with. Color does as well. But we must never also forget, and I always keep coming back to this, that probably the greatest theoretical physicist that this country has ever produced, alongside Newton, Paul Dirac, invented fermions in the sense that he defined them absolutely precisely as objects that arise from what's built in here, namely local gauge invariance, but primarily what's behind that even, Lorentz invariance. Flavor and color related to Dirac fermions were labels that Dirac could put on but didn't understand them in quite the way we understand them now. He even forecast that we will be able to label fermions. So the basic background to the way we work, and I'll be dwelling on this, is through the idea of spontaneously broken symmetry, spontaneously broken invariance, which has a relationship to what is called renormalization, which for an experimentalist is merely the statement, I beg to be challenged over this, but actually we have a Gauss law, which is essentially a sphere, and we have spherical symmetry. It's no more than that. But in that context, what comes tumbling out of a theory based on these principles are leptons, Dirac fermions, quarks, Dirac fermions, bosons, interspin objects in terms of Lorentz invariance, mass, and the idea of self-coupling in fields, which doesn't arise at the most elementary level in terms of fields, and that we've built a standard model of physics on this rigorous basis, which forms the basis of the origin of physical law, and it's valid as far as we can see at the moment, and I'll show you the good evidence for this, over a distance scale of something like a fifth of a Fermi or less, over to, if we believe the size of the universe as we stand at the moment, that sort of dimension. Now that's a pretty good thing to be able to say at this stage. One of the things that as an experimentalist one keeps coming back to is how this was all achieved, and of course the theorists keep telling us it's all based on symmetry. So then you really start to penetrate with theorists, and in that context what you do is a statistical measurement. If you have a bunch of theorists who are expert in your field, and they're all sitting in front of you, you make a controversial statement, you measure the number of heads going horizontally, the number of heads going vertically, and the number of heads not moving, and you come out with an expectation value. So I'm an experimentalist. Challenge me on that, theorist. I'm sick of theorists saying, this is the way it is, John, when someone else said, this is the way it is, John, and they're two completely different things. Never mind that. So in terms of what essentially we experimentalists carry away now, in terms of how we've moved on, is that there is symmetry. Symmetry is a nice thing to have. In the case of a building with towers, it's absolutely clear, broadly speaking, these towers are vertical, they go up, they're aligned identically, so in terms of those simple characteristics, they're all the same. There's symmetric, there's uniform order. There is actually, in the part of the world where I come from, or where Peter comes from, a very nice example that you can build your thinking on as an experimentalist, and one drives past it if one wants to go up into the beautiful country in the north of England. There's a place called Chesterfield. Chesterfield has a cathedral, and the Chesterfield Cathedral has the characteristic that the architect designed it such that it didn't have this symmetry. Well, actually, the builder built it. I'm sure the architect designed it with the symmetry. So basically, its spire is not quite upwards, it's leaning, and as a consequence of leaning, there's no preferred direction of lean, presumably. If this particular architect had built lots and lots of these cathedrals, it would have been a particular builder, I should say, with his tendency to lean, and presumably was spanning round before he built them, they would have all went in purely random directions. We would have had many of these Chesterfields. In fact, there is uniform disorder, there is, if you like, degeneracy, there's an equal possibility for any lean, there's symmetry again. To an experimentalist, that comes back. It comes back to the fact that when he learns about his quantum systems, molecules for example, they have degeneracy in their lowest state. There's uniform disorder, if you like, but all with the same energy. There's an equal possibility for any of the states. The symmetry has been restored, even though it doesn't appear in the single, in one single state, when that's the ground state, and there's no such degeneracy. Fine, but I think we all accepted that 40, 50 years ago, but what's actually happened in what I'm taking you through is that, in fact, there is a second situation that could have occurred with that builder. That builder could have actually built all the Chesterfields and had a compass with it. And he could have built them all leaning in the same way. Not quite upwards, leaning. Many Chesterfields again, but with one preferred direction of lean. And in doing that, he would have had an asymmetry. Yet they were all the same. Each one is asymmetric. They're all pointing in the same direction. But they're sort of symmetric. They're symmetric with the asymmetry. That implies an order parameter from the lean direction. And on the basis of that, and this is what we experimentalists take away from what's been achieved over 40 or 50 or 60 years, I advocate, because that's what the theorists use and what we actually now see in our experiments, is that we should look at this in a bigger way than has been looked at 50 or 60 years ago. What we should do is imagine that this is the north of England part of the universe that I come from. That's another north of England in another space, and another space, and another space. They're all correlated in each space, and in fact the ground state has an even bigger degeneracy than we thought, and we're only observing one of the states. We're confined, we're inside part of the space of where the states are. There is a hidden symmetry because we are only sitting here, say, but that exists somewhere, that exists somewhere, that exists somewhere. And even those experimentalists, I like to think we can measure everything, probably were stuck somehow, only somehow inferring that. And that's what's come out of, essentially, that's essentially the confirmed consequence of the theoretical hypothesis that's come out of what I'm going to be mentioning briefly, which is the discovery of the Higgs boson. We see that. There was a spontaneous choice of the parameter. We happened to live with a builder who pointed his spires in one direction in this particular world, or universe or whatever, and in all the others, the same builders pointed them in another direction, purely randomly. So in fact, such a situation does have a symmetry. It has a hidden symmetry. It has the spontaneously broken symmetry. So if we actually look then at what's going on, we have manifest symmetry of a field. If it's a singlet scalar in its ground state, under the transformation concerned with the symmetry, and it's non-degenerate, there is a singlet coupling, one way it behaves, one property that we can measure. If it's a multiplet under the transformation, then there's a degeneracy. Multiplet states are observed, all members of the same reduced representation, the same group structure. It has reduced coupling, but also it has a reduced coupling for that group, but different couplings through some of the normal relationships between those states, and we can see mixing between those states. This is something that goes on all the time in quantum physics. The hidden symmetry of the field, on the other hand, has a multiplet under transformation, as here. It's degenerate. One of the multiplets of the states is us, so we see an asymmetry in the sense that it's not a perfectly populated, uniformly findable member of that group. One of the multiplet states observed is what we can work with, for which we can measure reduced couplings or coupling or couplings. We can measure mixing if it's around. There is an order parameter of that particular property, the order parameter being the builder of the particular set of fields that we have working for us. We are observing in this world nature, but from within. And I think that's the conceptual thing that we as experimentalists perhaps are most proud of, that in the original theoretical idea, this is effectively what we're concluding. And of course, the man who first put this down was Steve Weinberg. These are the words, I'll read them out, they're worth reading out, from his Nobel lecture in 1979. We are in a cave, imprisoned by the limitations on the sorts of experiments we can do. In particular, we can study matter only at relatively low temperatures, where symmetries are likely to be spontaneously broken, so that nature does not appear very simple or unified. We've not been able to get out of this cave, but by looking long and hard at the shadows on the cave wall, we can at least make out the shapes of symmetries, which, though broken, are exact principles governing all phenomena, expressions of the beauty of the world outside. Those words, when I first read them about 30 years ago, I couldn't make head or tail of. And as a slow, pondering experimentalist who plays around with pieces of kit and makes measurements, this has sort of dawned on me in 30 years as I've watched the results come out, and we've seen the relationships between these couplings work on the basis of that picture of hidden symmetry, just how far-sighted Steve was. Now, in essence, I could dwell on the next few things, but time always ticks on. This is sort of standard mantra if you try and learn and understand this sort of stuff, and that is that if our world was the inside of a superconductor, then it's all there just by replacing words at particular points. In Steve Weinberg's Nobel lecture, we are essentially, if we were living in a superconductor, then we would see an electromagnetism that wouldn't have the properties that we see now. We would know no better. We would see essentially an electromagnetism in which there wasn't an infinite range, a 1 over r squared field law, and all that sort of stuff. Because we were inside that world, and as any physicist will tell you, he believed in induced currents and shielding and what have you, but he wouldn't know better. That's looking from within. So I don't have to dwell on this too much here. Essentially, inside the supercurrent, inside a superconductor there are supercurrents, there's zero resistivity, there's a correlation. I want to mention this because actually the theory that then drove us towards a microscopic picture which explained the necessary order and what have you that goes on in a superconductor that confines currents and shields the world that we're in from having the electromagnetism that we know, was of course the VCS theory. And Peter and I spend a lot of time trying to put right an injustice in the history of this, and that is that one of our colleagues many years ago, who died 20 years ago, 25 years ago?
No, only 10 years ago.
10 years ago.
7 years.
Yes, Herbert Fröhlich was actually in our department, and we had the privilege to talk with him once or twice, or 3 times, 4 times, a very deeply thinking man, and he essentially wrote down the pairing interaction that Bardeen, Cooper and Schreifer actually acknowledged drove them towards deriving the necessary order and correlation, if you like, the fact that the Chesterfields were built all in one random direction, that led to them then writing the Nobel Prize-winning paper that explained that on a quantum basis. But essentially, and this is not always brought out, if you look at how the manifestation of this fixed range electromagnetism occurs, it happens because you have to have this order, you have to be able to plug it into the equations of electromagnetism, acknowledging also that the ground state is like a whole group of Chesterfields. It's a whole bunch of paired electrons which have an order parameter, which immediately fixes the current you put in to have a structure like so, where you better also add in the scalar potential that's there. This is, if you like, the condensate, the correlated charge carriers, and this is the scalar field. And just in the beautiful structure here, which gives you all the normal laws of electromagnetism, you turn this equation, the ground state, into this equation, which just looks like electromagnetic fields with a finite range term. That is a very beautiful thing that now, because we've got the Higgs, us experimentalists can even perhaps spend a little time trying to understand. Forgive me for those of you who take this as very elementary. Now just let me dwell just a little bit on this. For those of you who are not particle physicists, if you take this spontaneous symmetry breakdown stuff and you put it together formally in a slightly more complicated way than a superconductor, you can set up a locally gauge invariant electromagnetic field theory. You can add in the long-range scalar field, and you will demonstrate that perhaps in the universe that you can spontaneously break the local gauge invariance, because we're only sitting in part of what is out there, and generate a finite range electrodynamics. It just works in the same way. In the case of a system where you set up more than one such electrodynamics, you can resolve things through what amounts to essentially the hypercharge, the flavor of what's going on there. You can put in your spontaneous symmetry breakdown, and you can come out with essentially an electrodynamics which is essentially, as we observe it now, infinite range. You can set up a piece of the theory as well, which has 3, not 1 vector boson, which are now massive in the sense that they give a finite range. And in fact, what you have got at the end of it is just your spontaneous symmetry breakdown manifesting itself, as we sit inside our confined world, as a theory with 2 scalar fields in which we see it as an electromagnetism with finite range. And on top of that, one will find that this gauge symmetry is also related to the overall phase that often isn't measurable in quantum physics unless you have additional interference. This picture, which was actually set down in terms of the number of scalar fields and the number of vector fields, came from 2 British physicists, as well as 3 others, but these 2 were instrumental in writing it down, getting to the point where Peter Higgs was able to write it down as particle physics with this number of fields. I think is essentially the essence of the triumph of what particle physicists have now formally put into physics forever, in the sense of the major conceptual confirmation. When we turn it into the quantized version of what's going on, then of course what this amounts to is a local gauge invariance theory in terms of a triplet vector field and a scalar field as before, quantized now in terms of infinite range, therefore massless quanta in that field. 2 scalar fields, which actually are massless to start with. You do the spontaneous symmetry breakdown, and these become photons, Zs, and W bosons that we all talk about, as well as one scalar particle which still survives with this mix, and that scalar particle is the Higgs, which now has mass. And if you look at just the way you would write down a simple energy equation, or vector energy equation, for say a lepton or a quark, a fermion, then you would write it down in the case of this vector field, electromagnetism, plus the scalar field in this sort of form, whereby you've only injected these into the algebra in a way that maintains the Lorentz invariance. And that is, in essence, for the elementary experimentalist, what this Glashow-Solan-Weinberg, this electroweak theory is doing. Now, as experimentalists, that's just fine. We now understand what you theorists have been telling us for 30 years. We believe it because we've seen it. We are prepared to spend the time to try and understand it. But actually, we've always worked, when we do theory and compare it with experiments, we've always worked with just what amount to, in the quantized theory, the basic splitting functions, we call them, that are to be found between the quanta. Now, these splitting functions derive from the diagrammatic approach that you can work in perturbation theory, when you find that each splitting function amounts to a term in a perturbation theory. And this was all derived, of course, as everybody knows, by Feynman in quantum electrodynamics, and works through this coupling constant being small, because you don't need too many of these diagrams. And essentially the whole of what drives what experimentalists do is a kind of bloodstream knowledge of how these things and one other set work in terms of putting them together to observe the interactions we see. But before I go on, what I wanted to do was to just also put on the map essentially what amounts to the distance scale, where we are, how we are looking at what's going on with fundamental quanta, Dirac fermions, and the consequential vector bosons, and scalar bosons that drive the fields, the minimum fields that we need. What this means in terms of distance referred to scale. And this is a very, very sobering plot. It's the experimentalists making life hard for themselves because it's logarithmic. Don't show this to the minister. This is essentially what we're after, moving down in distance scale, moving up, according to the Heisenberg uncertainty principle, in terms of momentum, so we can get violent enough collisions. I'll touch on that just in a minute, showing you examples. We're trying to get down to a distance scale where somehow we believe that these theories are going to look the same. There's gravity, there's the strong force. I've actually only been talking about, in terms of the spontaneous symmetry breakdown, electrodynamics and the weak beta interaction coming together. If we actually look at where we stand now, we're pretty much at what's called the Fermi scale, where we've got our unification, as I've just been describing, of electroweak physics. We could write diagrams like this between fundamental fermions and bosons. We have here the strong sector that was describing nuclei, which we can't put together yet. We've essentially got here the point at which we can try and understand this and have a chance of understanding it in terms of a perturbative expansion, and therefore diagrams. This is where we were until 2 years ago experimentally. That's what we're aiming for. That's what the LHC gives us on a log scale. It's quite sobering, isn't it? We work in a linear world experimentally. We're actually going to be able to take ourselves down to see what's going on here in terms of the unified electroweak theory and this line coming in terms of chromodynamics, and to any extent that gravity might be linked to that scale. We're only moving down essentially an order of magnitude in terms of energy. Typically there's an order of magnitude in terms of position as well, in terms of what's going on. But that then, with that sense of where we are, we should also then mention that we also think as experimentalists in terms of splitting functions in the fundamental quantum field called chromodynamics, which I will come back and touch on very, very near the end. We have splitting functions again. They have essentially exactly the same characteristic. They're calculated out in terms of the perturbative theory, and they involve Dirac fermion, and vector boson. In this case, in chromodynamics, this guy here, the gluon, the vector quantity in the chromodynamic field theory, is itself not a singlet in the color symmetry, the chromodynamics that's involved, which is exact. And these are Dirac fermions, and these are massless, again, equivalent of infinite range type photons. We can work these out. They have a very, very simple structure, even though they look a bit complicated here. Their structure is very, very simple. We can carry them around in our heads, and we do, if we can go to what is very, very relatively small fractional momenta. That is the momentum of the quark carried out of the parent quark, PQ out of Q. We can carry them in our heads. They're essentially just constant or dx over x, depending on whatever is the off-shell particle. One of these final state, this is time ordered, but one of them is spaced in the other side of the light cone. This is the quark that is space-like. We can carry these very simple rules forward. You can't remember this. At low x, you get these very simple structures in which there are characteristic dependencies always in terms of dt over something, but the dx or the x over x just is associated with whether the off-shell guy that you split to is a fermion or whether it's a gluon. And believe it or not, that justifies essentially the energy dependence when you put these things into calculating processes. So that's the way we sit in handling our experiments. We sit with vector quantum field theory, which could be the electroweak unified theory, or QCD at high energy, and we try and understand what's going on. I'll spare you this. This is what goes for politicians, except for one thing. It's meant to point out to them that it is quite important to have experiments and to have CERN, because at the end of the day, your weight is more than 99% chromodynamic energy. So you get a laugh out of a politician if you say, if you go to the doctors and you ask for a slimming pill or something like that, and you explain your problem is that you wish to reduce your chromodynamic energy, it's probably not the case that you will get the right diagnosis. It is a sobering fact that we do have the mass we have because we are chromodynamic energy. Very little to do with anything else. Now, time is marching on. I just wanted to give you a sense of the scale of the pieces in the standard model. We have fermions, quarks that we presently put into this chromodynamics involving gluons as well. We have the bosons in the field theory, and we have the leptons, and we have typical mass scales across here that I've put on there. And I've now been able, as of for a month, to put a number in here for the Higgs, which will play the role, as you'll see very shortly, of the last piece, as I explained in terms of spontaneous symmetry breaking that we observed. I will just jump over this. This is really in essence, to point out to anybody who doubts this that you can do your interference just collecting individual photons, and if you just build up statistics, you'll end up with what you observe on a piece of paper. But the essential message I want to get over to you from this is that in the experiments we do, in which we collide particles head-on, we actually are able to trigger. Just one second. Do I have this? No, it wasn't on there. Excuse me. We actually are able to see these interactions, and we are interested, obviously, in understanding the probability amplitude for a particular interaction, in which a particle 1 and 2 goes to a 3 and a 4. Whether those particles are the actual particles we control in the interaction, and whether 3 and 4 are the only particles that come out of the interaction, and manifestly they're not when you've seen pictures of the LHC, we're always confronted with the fact that this amplitude involves something which characterizes the probe, something which characterizes the target, and the interaction. And there is spatial structure in each of these. The structure of the probe, there's a matrix element which has a spatial extent, and there's a structure there. We work in terms of conjugate variables in that the spatial structure is related to the transverse momentum that's involved, which means that the most violent interactions are the things that we want to see, which actually means that when you're doing your interference, you want to see these pieces and how they differ from experimental observation, from theoretical prediction, to understand what might be going on really at the smallest distance whenever you do have, in this case, light hitting a diffraction, whatever it is, or a proton hitting a proton, or an electron hitting a proton, or whatever. Just to prove to you once and for all, I mean, here's a picture. We all do this when we're undergraduates. Here's the Compton effect as drawn out. What Compton actually was essentially doing was observing gamma rays individually. At the LHC, 70, 80 years on, we're doing exactly the same thing. We're colliding protons with protons, and something is happening in the interaction which produces species at wide angle to the beam collision axis, which were the edges of that diffraction distribution. And what we've been doing since 1950, as we've built up the expertise, we've been colliding protons with protons, electrons with protons, electrons with positrons, positrons with protons, and so on and so forth. In every case, we have to be able to extract the structure and the scale of the probe, the interaction and the target. And that is actually not an over-constrained situation, so we actually have to measure interactions between different combinations such as we can control them. I've probably spent too much of my time working on, but it was also big, and in fact it's about the same size as the CMS experiment, one of the colliders of the LHC. It's a typical, well, not a typical person, a particularly special person. Here's a typical person. Large complex detector. We trigger, just like Compton did, individual interactions, and we record in the detector. This particular experiment involved electrons colliding with protons, and the electrons had lower energy, lower momentum than the proton, so things were thrown in that direction. We have stored beams, and when bunches cross, individual quanta interact. We trigger on the basis of what we see in terms of tracks and energy deposition. Very quickly, we can see balance in the sense of clearly we're conserving energy and momentum at some level where we can measure it. We have detectors that leave tracks and don't disturb the particles very much, and we have detectors that actually hit something substantial, and we have ways of recording the way that energy is deposited. We don't actually make craters in our detectors, but never mind. Essentially, in this particular picture, an electron, which is a beautiful Dirac fermion, is hitting a proton, which is an extended object. And so what we talk about is what happens to the electron. This one turned right round. It's actually a classic Rutherford scattering, backscattered probe of a target. This time the target's herring at it with something like 500 times the momentum of this electron. Thus things tend to be thrown in the back direction. We see when we look in that way or in that way, we can see balance. We can see an electron scattered. We can see recoiling particles clustering rather than spreading out and also balancing that momentum. This suggests something is at the root of what we call a jet. We can actually then associate with those splitting functions and diagrams we can build what we think are the fundamental interactions that are going on, and where there are collections of interactions that constitute the structure of the other particle. So, for example, this is the sort of guiding diagram that we would draw, and we would say a fragment of the proton, most likely a quark, in fact certainly a quark, given that the electrons scattered off it, has happened here, and there are pieces here of the remnants of the proton that just don't get out to wide angle and carry on in the beam pipe at the edge of detectors. We can actually look at momentum conservation. We can have two jets sometimes and an electron, and these two would add up to balance that in that direction, to balance each other in that direction. So we can build up topologies of more than one of these jets, more than one parent, whatever's going on in there. We can go on and associate these jets with quarks and gluons by doing analysis and trying to understand the way the hadrons and the particles come out. That allows us to put together the pictures we make from these splitting functions based on the basic theory, because we've got one particle in this particular experiment coming in whose interaction we do understand in that electroweak theory, and another who's got lots of structure, and even the pieces inside that structure have their own spatial extent by virtue of the field theory working in action in their world. So in fact, we have something that we think we now can work with to try and understand what's going on, except that much of the time we see things balancing every now and again. Something's not balancing here. There is something missing. The electron proton have interacted. In fact, when you look end on, you see there's nothing against the electron. It's really remarkably empty. That constitutes the inferral that if we had balance, something went out there. And of course, in terms of our electroweak theory, which we were bestowed to us by Glashow, Salam and Weinberg, we essentially interpret that as a positron interacting and producing something going out that we can't detect, a neutrino. So we can see the pieces of the standard model in modern experiments now in a way that we couldn't see them before. We call them neutral current and charge current interactions. We can see how our splitting functions can go in to make calculations about what's going on. We can understand these parts of the interaction, whether they are neutral current, that means an electron or a positron going to an electron or a positron, or an electron, excuse me, these arrows back to front, electron or positron going to a neutrino. We can see how these interactions are put together within the context of the Glasgow-Summerall-Weinberg theory and the degree to which we are probing it in terms of the distance scale here. So we really test it, whether it really works, whether those reduced couplings fit together that we measure and analyze for, built on the fact we use the splitting functions. And we have situations in which the probe scale can be greater than or less than or equal to about the interaction size and even the target size, because in the case of the photon, this probe can actually be a long-range interaction, an electromagnetic interaction. So the issue there is one has to be careful and understand that. And we can then also learn about the dynamics in the target. These quarks are coming out of protons, and we can try and understand them in terms of splitting functions that we would put in terms of what really came out of the proton, how it came out of the proton, and how it subsequently may split and interact before what's going on here gets to actually couple to it. So we learn about the color dynamics. This is history, really. This is when I came into the subject. This is 1969, 1970, 1968 actually, at Stanford, where people were doing experiments with a beam and a spectrometer, and came up with a startling result after, in early 1960s, Hofstadter had measured the elastic scattering of protons. Just this constant dependence on a particular variable, I have no time to go into it, was the first evidence for the statement that the proton was made up of quarks or something point-like. Interestingly, we experimentalists are cautious beasts. If you read the proposal for this experiment, it merely has in it the statement, it's important to do the experiment because it's a general survey of the basic cross-sectors which will be useful for future proposals. And it won a Nobel Prize. I'm nearly done. I will skip over that. I will just show you that when we now look for something that is flat, we can now measure it with such precision that we can see it's not exactly flat depending on one of the variables in the splitting function. It rises in certain regions and it falls in others, and that tells us, if we put all this stuff into these measurements, what actually the proton's made of. And here you have it. These are essentially the gluons in matter. If you multiply that by 20 relative to these guys, well, not this guy, you can multiply this by 20 as well, but relative to these guys, you can see that when you integrate it all up, that's why you're 99.99% field energy. I'll skip that. This is the one that I really wanted just to focus on in view of what I was saying. This is essentially the definitive measurement that when you scatter an electron off a proton, you see that electroweak theory in all its unification bar one feature. You see when an electron scatters to give an electron and slush. When you hit one of the quarks, you see something that falls like 1 over q to the 4 until you start to run out of energy. In the case of an electron turning into a neutrino, many orders, 3 orders, 4 orders down, you see something that turns over, has the same strength as the photon, and then the Z0 exchange here, the W exchange, so you have the unification in the Glasgow-Summerall-Weinberg theory. It's all put together in terms of the curves which come out of that spontaneously broken symmetry picture of how we maintain our symmetries. We see here the electroweak unification in an experiment, unambiguously, uniquely, in evolution from very low scale, where if you like beta decay, which is the weak interaction, is way below electromagnetic interactions, to where they're the same. New experiments now at the LHC are much bigger. I have no time to talk about these. This is a Higgs candidate when a proton hits a proton from last July. Spectacular events, and this is only a tenth of the story. There were many, many more hits for which these tracks had to be dug out. And photon detected there and photon detected there, so that Higgs was sort of moving out of the interaction point in that direction as it decayed. This is one of those beautiful plots experimentally one could hope to see. This, just in case you haven't seen it, is exactly what you would expect to see if that standard model with its W's and its Z's and everything else in its gluons and whatever worked, but we still haven't got to the point where we were detecting a Higgs boson. I mean, it could be anywhere in mass. And this is where now the LHC has got on one of the 2 experiments. Very clearly, you see an excess above that at a mass of about 126, which is why I could put it in. And you can start to measure the reduced couplings as such, and you see that if you plot against 1 what you expect from the standard model, but you look at these separate, 1 is what you expect with the mass of 126, and 0 would be if there was no Higgs. These are the different possible decay channels, so in all those complicated interactions you can dig out single interactions and look at the samples of them and measure these couplings. The degree to which these points are inconsistent with this line would be the degree to which the particle one sees is not consistent with that scalar, that Higgs, in that spontaneous symmetry breakdown that we were looking for, that people were looking for. If I may just have 1 more minute, is that all right? I started late.
Even so, you've still got over, but just very quickly.
I just wanted to say, well, where do we go from now? More from inside. It seems to me that we really have reached the landmark now, in which way it's a pleasure to talk to people with your experience, your expertise. We have found answers in new fields and symmetry in the last 50, 60 years. We've produced a theory which works in pretty well all aspects, and there's nothing beyond what we see so far. It involves scalar fields for the first time. When one teaches electromagnetism now, one should be teaching it as part of a theory with electroweak W's and Z's, and also the Higgs field. It's all part of electromagnetism. If it's not in the future going to be something like this, what is it going to be? I haven't a clue. After all, we've been living with fields for all this time. But in going there, we have to accept the idea that the quantum vacuum isn't nothing, it's something, because it has this essential asymmetry, and that was what was driving Weinberg to say that we were working in a cave. That's given us some idea of how we can put mass into a theory, but what is mass still? Where is gravity? Why is there, and what is mass equivalence? How is this related to the Higgs field, which was what I've just shown you we've seen evidence for? Why are there 3 generations of quarks and leptons? Where does QCD sit in all this? We're nowhere near that. But Dirac would say, of course, quarks and leptons are fundamental. If not, do they have substructure? In fact, can Dirac's beautiful fermions have substructure? These are things that we have no answers to, and I've nearly finished now. I'm going to skip all this, except
that we have to finish now.
Scalar field and gravity. There are ways of doing experiments to test this, and I finish. I think what we've got to at this point is a triumph in the history of physics. We've really come to a marker.
Okay.
Thank you.
Thank you very much. So, any questions about to be able to break, because we're running very late.